Chapter 2 Molecules, Atoms, Molecules, and Ions. Look around at the great variety of colors, textures, and other properties of the materials that surround you. The colors in a garden, the texture of fabric in your clothes, the solubility of sugar in a cup of coffee, or the transparency and the beauty of a diamond. The materials in our world exhibit a striking and seemingly infinite variety of properties. But how do we understand and explain them? What makes diamonds transparent and hard, whereas table salt's brittle and dissolves in water? Why does paper burn and why does water quench fires? The structure and behavior of atoms are key to understanding both the physical and the chemical properties of matter. Although the materials in our world vary greatly in their properties, everything is formed from only about 100 elements, and therefore from only about 100 chemically different kinds of atoms. In a sense, the atoms are like the 26 letters of the English alphabet that join in different combinations to form an immense number of words in our language. But what rules govern the way in which atoms combine? How do the properties of a substance relate to the kind of atoms it contains? Indeed, what is an atom like, and what makes the atoms of one element differ from those of another? In this chapter, we examine the basic structure of atoms and discuss the formation of molecules and ions, thereby providing a foundation for exploring chemistry more deeply in later chapters. Section 2.1 The Atomic Theory of Matter. Philosophers from the earliest times speculated about the nature of the fundamental stuff from which the world is made. Democritus, 460 BC, and the other early Greek philosophers described the material world made up of tiny indivisible particles they called atomos, meaning individual or uncuttable. Later, however, Plato and Aristotle formulated the notion that there can be no ultimately invisible particles, and the atomic view of matter faded for many centuries, during which Aristotelian philosophy dominated Western culture. The notion of atoms re-emerged in Europe during the 17th century. As chemists learned to measure the amounts of elements that reacted with one another to form new substances, the ground was laid for atomic theory that linked the idea of elements with the idea of atoms. That theory came from the work of John Dalton during the period from 1803 to 1807. Dalton's atomic theory was based upon four postulates given in Figure 20.2.1. Dalton's theory explains several laws of chemical competition that were known during his time, including the law of constant composition, based on postulate 4. In a given compound, the relative numbers and kinds of atoms are constant. It also explains the law of conservation of mass, based upon postulate 3. The total mass of materials present after a chemical reaction is the same as the total mass present before the reaction. A good theory explains both facts and predicts new ones. Dalton used his theory to deduce the law of multiple proportions. If two elements A and B combined to form more than one compound, the masses of B that can combine with a given mass of A are the ratio of small whole numbers. Dalton's atomic theory. Number 1. Each element is composed of extremely small particles called atoms. An atom of element oxygen, an atom of the element nitrogen. Number 2. All elements of a given element, all atoms of a given element are identical, but the atoms of one element are different from the atoms of all other elements. Atoms of oxygen, atoms of nitrogen. Number 3. Atoms of one element cannot be changed into atoms of another element by chemical reactions. Atoms are neither created nor destroyed in chemical reactions. Number 4. Compounds are formed when atoms are more than one element combined. A given compound always has the same relative number and kinds of atoms. Figure 2.1, Dalton's atomic theory. John Dalton, from 1766 to 1844, the son of a poor English weaver, began teaching at age 12. He spent most of his years in Manchester, where he taught both grammar school and college. His lifelong interest in meteorology led him to study gases, and then chemistry, and eventually atomic theory. Despite his humble beginnings, Dalton gained a strong scientific reputation during his lifetime. We can illustrate this law by considering water and hydrogen peroxide, both of which consist in the element hydrogen and oxygen. In forming water, 8 grams of oxygen combine with 1 gram of hydrogen. In forming hydrogen peroxide, 16 grams of oxygen combine with 1 gram of hydrogen. Thus, the ratio of the mass of oxygen per gram of hydrogen in the two compounds is 2 to 1. Using Dalton's atomic theory, we conclude that the hydrogen peroxide contains twice as many atoms of oxygen per hydrogen atom as does water.